This will be a recorded lecture so that after the lecture ends, if you want to revise it, you can directly go to your GCR and you will have access to this lecture. Okay. So I think a reasonable number of people have joined. Okay, please let me know if you can hear me again. And is this visible to you?
Yes, sir.
Okay. Okay, so I think we should start. All right, so last time we had completed this example. Please let me know if the screen is still visible or not. Uh, can everyone hear me?
Yes, sir.
And is the screen visible to you, all of you?
Yes,
Yes,
sir.
sir.
Okay. Okay, so last time we had discussed this example in which I had cleared you that during when we will be interested in finding out the hydrostatic force on a curved surface. So normally before that we were discussing only a flat surface which was not curved. Okay, so like a rectangular plate or a circular disc or a triangular shape. In this, we were only interested in two things: the magnitude of hydrostatic force plus the yp, which was that point on that surface where that force was acting. Okay, so this is the front view. In side view, it was something like this, and that yp was somewhere here. Okay, or even somewhere here. Okay, but now on a curved surface, we have that FR, that YP is still there, plus there is also another thing which is theta, the angle at which your resultant force is acting. Okay, so last time we had some confusions, so let me clear you that this is still valid. All of this is valid, and the process of evaluating the YP, or the point at which your force will act, is still the same as it was in the case of plane surfaces. Okay, so I hope this is clear. Again, we will take this surface as we did last time, and we will find out YP using the same formula. YC is S plus B by 2. So S is known to you, S plus B by 2, we can easily find out. This is the value. And I double X, because it is a rectangle. If we look back, this cylinder, if we look it from the front view, it will be like a rectangular plate cut in half. Okay. So this cut in half from here, because the water is only touching the cylinder till this point. This is the point A, looking from the, this is the side view, and this is the front view. Okay, so the water is only uh, in contact with the surface till this point A. Okay, so it is a rectangle, so we will assume this is A, which was I think 1, and this is B, which is 0.8. So I double x will be a plus b cube divided by 12. Okay, so clear. I hope this is clear. We will find this value and put all these values here, and we will get that point in y direction on which this force is acting. Okay, so now in this case, curved case, we have Fr, the magnitude of force, the theta angle, and that Yp. uh, in the previous case, flat surfaces, we only had the resultant force and this yp. Okay, so I hope this is clear. uh, Next subtopic of these hydrostatic forces and the last topic of this chapter is buoyancy and stability. So, have any one of you heard the word buoyancy or buoyant force?
No, sir.
Okay, so let's take an example and let's see what is this buoyant force. So we are quite clear that when a body, an arbitrary body of area A, is submerged in a fluid. Okay, so the top surface, which is this one, and the bottom surface, which we cannot see from here, will experience some forces, right? Is it clear to you guys? Due to the pressures. Okay, so if I take the side view, from the side it will be something like this, and there will be some pressure, there will be some force due to pressure at this point. Let's call it F2 for our ease, and there will be some force at this point, and we call it F1. Or at that there will be some resultant force acting on this whole area. I'm talking about that hydrostatic force. Okay, so just wait a minute. Okay, so we will just give me a minute. All right, so I was explaining there will be some force acting on this point and on this area as well. So, the knowledge up till now which you have gained from this chapter, can anybody tell me if the fluid density is constant, which force will be greater, F2 or F1? The area is same.
F2.
F2. Who said that? Kindly, please tell me your name.
Afan Mahmood.
Hassan. Okay. Afan. Okay. So, Afan, you're right, because the hydrostatic pressure, we know that the hydrostatic pressure acting here on the bottom surface will be higher. The reason is because anyone else, can anybody tell me why the hydrostatic pressure on the bottom surface will be higher than the upward surface?
Because as we go in depth,
Hmm.
hydrostatic pressure increases.
Yes, right. Good. Okay, so as we move downwards in a fluid with increase in depth, the hydrostatic pressure increases. Okay, so now we are only interested in these two forces. There is a specific reason. Let me just change the color of marker. Okay, so up till now we have not talked about these two sides. There is a specific reason because under the only the action of gravity, which is down acting downwards, and there is no other fluid motion, we will only experience these two forces, because resultant forces, because if we look at these two surfaces, the pressures acting on both points, they will generate a resultant force, but it will be equal and it will cancel out. So there will be no motion either in this direction or in this direction. I'm talking about a stationary fluid. I'm not talking about fluid dynamics. Okay, so this is a stationary fluid. We are talking about fluid statics. Okay, so this means that resultant. Okay, so Afan we had told us that the resultant force, the F2 is greater than F1. So what does that mean? It means that the resultant force will act in which direction if we sum take sum of these two forces. What will be the resultant force and what will be its direction? This is F2, which is greater in magnitude. This is F1, which is smaller in magnitude. So what should be the resultant force's direction? Upward or downward?
Upward.
Upward, because ultimately F2 is greater than F1. This means that there will be a resultant force which will act in the upward direction. Okay, so this is that force which is known as the buoyant force. Okay, so this is the force which acts on a submerged body in a fluid, and it acts opposite to your weight, the weight of the body. Okay, so let's see its mathematical expression and how we can correlate it with the fluid. Okay, so um, fluid exerts an upward force on a body immersed in it. That upward force is actually that F2 minus F1. This force that tends to lift the body is called buoyant force and is denoted by FB. Okay, so this is that FB. Uh, the buoyant force is caused by the increase of pressure and depth. So I already told you this point, and it is equal to, how can we formalize it? So it is equal to F buoyant is equal to F bottom or F2, which was F2. This is the force F2, which I was explaining. And then F1, F top minus F1. Okay. So this F bottom will be, so what is the equation for a horizontal surface immersed in a fluid? It is simply rho g H times A. Okay. So rho of fluid, density of this fluid. We are not talking about this material. Okay, please note that. Then G is the gravitational acceleration. This S plus H minus. Okay, so here this is actually the first force. This one, which is acting downward, which is acting on the downward surface, but in the upward direction. Okay, because it is a reaction force. Then we have rho g. Okay, I hope this is clear that why is it rho g s a and why is it rho g s plus h a? Because this depth is added. Okay, this depth is added till this point, while here it is only s. So we are taking this point. This is the depth for this force, while this is the depth for this force. Okay, when we will subtract it, so rho g is constant, area is the same. These two areas are same. Same by same I mean their magnitude is same. Okay, so we have taken it common and we have solved it. So we are left with this value rho g h a. Now tell me, what is this h times a? What does this indicate? H multiplied by a. What will this h multiplied by a give us? Anybody? H is the height of this body and a is the area, cross sectional area. So h times a will be, anybody? It will be equal to
Volume.
volume of this body. Okay, so it is the volume of this body. So this is actually that volume. Plus another thing. Okay, what will happen if you take a glass, okay, its initial uh, the water was filled with glass and its initial uh, point was this one, okay, the height was this one, okay. So if I so it will have a specific volume, height and specific diameter, okay. And if I place, what will happen if I place a solid body inside it? What will happen to this water surface? It will rise.
Level of water increase.
Yes, the level of water will rise. Okay. So this means that apparently, I'm talking apparently, the volume of the fluid body will increase, right? But that is apparent. That is not the actual case because this body is solid body, and due to addition of this body and this fluid, the volume has risen. Okay, and this rise in volume is actually equal to the volume of this body. Okay, so if we know the volume of this body, we can find out that how much volume has been replaced. That will be the same. Similarly is the case with this value. Okay, so this volume which has been replaced by this body, because if we dip this body in the fluid, definitely uh, it will occupy a space and it will have a volume. That volume is equal to the volume of fluid displaced. Okay, so we can also say that for this case, that this body has displaced this much fluid volume. Okay, and it will be equal to the weight of the fluid, displaced fluid. Okay, so this buoyant force is equal to this one. Okay, I was it is also equal to the weight of displaced fluid. Okay, so buoyant force is equal to the weight of displaced fluid. Okay, so this is the outcome from this whole thing. Okay, so where V is the volume of submerged body, that is equal to the volume of the fluid displaced by the submerged body. So this is still valid, which I told you. So hence we conclude that the buoyant force acting on the plate, this plate, is equal to the weight of the liquid displaced by the plate. Okay, so this buoyant force FB will be equal to the weight of liquid which was displaced. So when I was initially telling you that in a container, if you have this delta, if you have added an ice cube, for example, and it has risen the height by this delta H. So if you calculate the weight of this water height, you will get the buoyant force. It will be equal to this buoyant force. Okay. So now the next thing is okay. Now let's see. We have okay. So this is the formula. FB is equal to rho GV, or weight of the displaced fluid. Okay. So for a fluid with constant density, we are talking about constant density. There are no fluids with different densities. Okay. Burn force is independent of the distance of body from the free surface. So the buoyant force doesn't depend whether your body is somewhere here or in the depth. if the density is constant, please note that it is also independent of density of solid body. So the buoyant force even for a cube made up of wood, if you have placed this at this specific depth or somewhere here, if the same cube made up of steel is placed at this point, both will experience the same value of buoyant force. Okay, that buoyant force does not depend on the density of the solid body, it only depends upon the density of fluid. Okay, and the definitely the volume of this fluid, it is also dependent volume of this solid body. Okay, so Archimedes principle you have already uh, seen somewhere in your ninth or 10th class or first year second year, you had already been gone through this term Archimedes principle. So what does this indicate? The thing which we have already studied, it is the same thing. The buoyant force acting on a body of uniform density immersed in a fluid is equal to the weight of the fluid displaced by the body, and it acts upwards through the centroid of the displaced volume. Okay, so if you remember, you have already done an experiment related to this Archimedes principle, most probably in your ninth, 10th class or first year, second year somewhere. But I don't know whether you have done it or not because you are all COVID babies. So most probably there is a chance that you may have not done these things. Anyways, you will most probably perform an experiment related to Archimedes principle in your FM fluid mechanics lab, hopefully. Okay. So for
तो
floating bodies, the weight of the
फ्लूइड की
entire body. G, sorry.
अगर फ्लूइड की डेंसिटी चेंज कर दें हम तो फिर ये नहीं होगी buoyant
If
force.
your fluid density changes, this means that this will change and new buoyant force will rise. So higher denser fluid will have more buoyant force acting on the body. Okay?
Yes, sir.
Okay. So for floating bodies, the weight of the entire body must be equal. Okay, now this is something which we will see in detail, in a little bit detail. So, if a body wants to float inside the fluid, okay, at any given height, we are talking about floating. Floating doesn't mean that it is sinking or coming upwards, it is floating at a constant depth. That is only possible when the weight of the body is equal to what? Buoyant force or the weight of the fluid, displaced weight of the fluid. This condition must be met for the body to float inside a fluid. Okay, so this is that condition, and if we simplify it, we get this value because weight of the body will be rho density of body g v body volume of the body, and that is equal to rho fluid g times volume displaced. Okay, so this is your equation, which is very important and very useful and also very simple to understand. Okay, so actually, this is more of a constant term, and we can directly, let's say, I want to submerge of specific body with a density rho b. Okay, and the density of fluid is also given to us. So we can directly see by this fraction that what will happen to the body, whether it will stay at a level, whether it will sink down, or whether it will float upward here, somewhere here. Okay, so if this term, this row of body divided by this row of fluid, is less than 1, okay, so the body will float. If this is equal, that means it is equal to 1. This means the body will remain suspended at any depth where you will want it to be. Okay. And if it is greater than 1, then it will sink down. The body will sink down. Okay. So this is a general criteria through which we can easily see how will a specific body will experience drowning. Okay. Okay, so we have a very simple example related to this uh, topic. A crane is used to lower weights into the sea where the density is equal to this one. Okay, so the sea density is 1025 kgs per meter cube for an underwater construction project. Determine the tension in the rope of the crane due to rectangular concrete block. Jiski density is given to us, which is the density of concrete 2300s. When it is number one suspended in the air, number two completely immersed in water. Okay, so the first we need to find out this Ft when it is suspended in the air, and then Ft when this concrete block is completely submerged in water. Okay, so the first case is very simple. First, we can find out the volume of this cube. All the dimensions are given. So this is the volume, 0.48 meter cube. Next, in case of the fluid suspended in air, okay, so in air, we can simply find out by using the simple formula, that is the tension, this tension force will be equal to the weight of concrete block. We are ignoring any kind of other force acting on this concrete block. So we can easily find out the weight of this concrete block by using rho mg, and m is equal to rho times g, rho v, sorry, rho times v. So we get this force is equal to 10.8 kilonewton. Now what will happen when we will submerge this block in this liquid or this fluid water? An additional buoyant force will act on the body, okay, and here this Ft will be equal to weight minus Fb, okay, so this weight minus Fb. So this tension in the string will be lowered by a fraction of this Fb. And how can we find out this FB? Simply rho GV. V is the same volume of the cube. This is also the volume of the fluid that has been displaced times G. But the density which we will use here is the density of water, seawater. So this is that 4.8 kilonewton. And if we minus it from here, we will get the tension in the string or this rope when it is submerged inside the water. Okay, so this was a simple numerical problem related to buoyant forces. Okay, this last slide of this chapter. So how does we relate this stability to buoyant force? I mean to say, sometimes body sinks in water, but sometimes it remains, another body does not sink in water. So what is the criteria for that? So normally we want that the center of your buoyant force is upwards as compared to the center of gravity. We want this. Okay. If this is the case, that the buoyant force, the point at which your buoyant force is acting, it is upwards, and the point at which your weight is acting or center of gravity, it is downwards. Okay, so it will make what will okay. First, also understand that at which point this buoyant force will act. This buoyant force acts on the center of pressure. Sorry, uh, this buoyant force acts on centroid. Okay, so this is the point which I forgot to tell you. So it acts upwards through the centroid of the displaced volume. So displaced volume is actually this thing. This is that displaced volume. Okay. So the centroid will be, let's say if it is a circle, so the centroid will be in the center. Okay. But we cannot change the centroid of a body. Okay. But we can shift its center of gravity. Okay, because centroid depends on the shape of your body, but the center of gravity depends upon where your mass is more concentrated. So if we change the areas, the mass concentration, we can shift the center of gravity. So I've told you that if the center of mass is upwards, this B is the center of mass, and center of gravity is downwards. This means your body is stable. Okay, this means if you disturb it, it will not directly sink. So what will happen if I disturb this body? Because buoyant force is acting upwards, so if I disturb this body, what will happen? Let's say by disturbance I mean that I have displaced this body somewhere here. I've twisted it like this. Okay. So what will happen? Due to that twisting, this place, this heavy, because this is weight. So this has come here, and the point B is here, and G is somewhere here. Okay. So I have twisted this body. Now what will happen? This FB is acting upwards while this weight is acting downward. It will generate a reverse movement and it will stabilize itself. Okay, in this case, number one, stable case. But if this B is downwards, for example, in a case where you have with the same uh, body, if you had twisted it further up till this point, or any body which has a weight upward here, so its center of gravity is shifted upwards. Now what will happen if you disturb it? This G will come here, this P will be still be here. Okay, but in the direction of disturbance, a supporting moment will be generated. Okay, so this will be like this. So it will twist the ball further or the body further. So it is an unstable case. This is a stable case. And we also have a neutrally stable case where the body center of gravity and buoyant force both are at the same point. And this is called neutrally stable. Okay, so this is basically this condition, I guess. Okay, so normally the boats and the bodies which need to travel on the sea have this condition. We want it to have this condition. Okay, so that if any kind of disturbance occurs, the boat stabilizes itself. Okay, so that was it for this chapter. So I'm sharing the chapter 3 problems with you as well, and hopefully I will upload the next assignment as well. Okay, so we'll stop the lecture here. Okay, so stop presenting. Okay, now I will take the attendance. Why has everyone left the meeting? Some of you. Kindly ask everyone to join because I will take the attendance. Okay, let me just first stop the lecture as well.